this week's Cron seminar. We only have one talk today, and our speaker is Liu Yang from UCLA. Liu Yang obtained his PhD in applied math from Brown in 2021, and he was advised by Professor George Kanatakis. He has been serving as an assistant adjunct professor in the Department of Mathematics at UCLA since 2022, collaborating with Professor Sunny Osher. Yang Liu, welcome back, and you may want to
Uh,
start the presentation.
okay, thank you for the invitation. So today I'm going to talk about my recent work on in-context operator networks, which is aimed to build like large scientific learning models. Okay, so this is joint work with Siting Liu, Tingwei Meng, and also Professor Stanley Ocean. Okay, so here's the outline of today's talk. So I'll first talk about in-context operator learning. What is that? I'll start from the motivation, and then talk about methodology and some numerical results. And in particular, I will introduce some generalization behavior. Okay, I'll also talk about multimodal in-context operator learning. So okay, here's the multimodal basically means the input with different forms. So actually, I will employ a language model like architecture, and then you can input physical knowledge with text. So it's not like just some data, but you can also input text, like how you can interact with language model. And also, I will show that some numerical tasks actually help the language model to understand text. I will also talk about forward and backward prediction of conservation laws. So that is basically an application of using icon. So in this part, I will basically focus on the discontinuity, the performance of discontinuities, because that is something I really care about for the scientific computing. And in the end, we'll have discussion. Okay, so I think the results mainly come from these two papers. The first paper has already been published on PNAS in September. So the archive actually even earlier, like in April, but yeah, the PNAS is published. And second paper is fine-tune language model as multimodal differential equation solver. We recently updated the title anyway. But the paper is also is published in archive in August. In August. Okay, and you can also access our code here in GitHub. So yeah, start from the motivation of in-context operator learning. So I want to have a quick review of the history of neural networks for solving differential equations. So I think the step one is like, okay, we will train a model to approximate a solution function, which is basically like function learning. And in this category, we have the celebrated freely informed neural networks. So that is George's work. And also deep Galerkin method, deep Rees method. So they are basically, okay, say, well, I want to use the neural network to approximate the function. And I can, and during the training, I'm solving this equation. Okay, that is what I'm doing. That is what I was doing. So the input of the model should be a vector, or in particular, for example, spatial and the temporal coordinates. And the output is also a vector, which should be the function value at this point. Okay. So, well, this stuff is definitely good. But the drawback is that you actually need to train or at least fine-tuning this neural network if the solution changes, right? So I think George really knows this stuff. So later, I think so the quant group did something like DeepONet. So DeepONet is like, say, okay, we want to train the model to approximate the solution operator, so that we do not need to train the model again for a new solution. But instead, we have this model taking the function as the input and output another function. Well, of course, you have discretization in certain stages, but this mindset is totally different. So this kind of operator learning basically says that once the model is trained to approximate the operator, then for a new input function, this input function can be the coefficient function, coefficient field, or the initial condition, something like that. You can just feed that into the model and get the corresponding solution. And you do not need to train the model again. That's definitely a step change. Yeah, so single model can be used for multiple systems governed by the same operator. However, I would argue that, well, you still need to retraining or fine-tuning for a new operator. For example, even if you change this equation a little bit, Like for example, there's some constants in this equation, and this constant is not part of the model input. And even you change this parameter even a little bit, the operator changes. So I really want to like make one step, even make another step further. Okay, so what is the next step? Okay. So yeah, so as a summary, so existing neural network-based methods for solving differential equations are limited by the equation specificity and need frequent training when switching to new problems. So we need models that can adapt to new physical systems and tasks, just as a human would. And I want to leverage commonalities shared across various tasks to improve accuracy and reduce data requirement. So inspired by large language models, we propose in-context operator networks. So I'm using a single neural network to solve a wide range of scientific machine learning tasks. And I can get rid of retraining, even fine-tuning a neural network when we encounter a new problem. Yeah. So this is the step 3 we are proposing. I want to train the model as an operator learner. So this model, instead of taking one function and output one predicting one function, actually takes these like examples, or you can basically view this part as the training data for the operator learning, like for the step 2 operator learning. But instead, now we are putting all this stuff as the input of the model. Okay, so this model should take like condition function 1, QI function 1, condition function 2, QI function 2 until like J pairs. And then what about and then now a new question condition? So the model should predict the question QI function. So it will learn and apply the operators in one forward propagation.
Yeah, and can you give us an example to understand, because it looks too abstract to me?
Yeah, that's exactly what I'm exactly like what I'm showing here.
Okay.
Yeah. So so operator. So before going to this figure, I want to like explain some terminologies, like operator mapping from condition function to QI function. So that is operator. Yeah. And what is example? Example is like a condition and QI pair. So that is what we call example. So the training, for example, okay. So in one training step, I will take okay, these are like J1 demos or release examples actually as input, and you can see it's like it's like, so this is one example, and this is like another example. Okay, in this example, it's like we're solving this hidden ODE problem. You have this ODE, and you have C1. Okay, sorry. It's the input condition is a C, and output is a U. So you see the function, and for each function C, you have a corresponding output U. So that is so C is the condition, and the U is the quantity of interest. Okay. So and the question about this example. So this is like this operator learning instance. So I will have an operator that maps. Yeah.
What is the query here?
Oh, I will introduce that later. Yeah, I will introduce that later.
Mm.
So this basically is an operator that maps C to U. Both are functions. So that is the operator here. So then the input or the prompt to the model should be the so like J examples. Each example is a pair of condition and QI, and what and a new condition or I call it present condition. Okay, I will feed this stuff into the model. And as for what is a query? So query is the is basically say where we want to make prediction of the question QI function evaluated as queries. So that's basically like the X inside the depot net. So that is basically X inside the depot net. Yeah, and Lula, I'm not sure if I answered your question.
Yes, it's clear.
Great. Yeah, great. So this is like one training instance, and for example, okay, we get into another training step. then we switch to another operator and perform this kind of training again. And we do it a lot of times. And after training, okay, now during inference, we can basically, okay, input some new examples corresponding to the new operator and ask the new question, and it should give me the prediction. So it will learn and apply the new unknown operator without any way out of it.
Yang Liu, sorry to interrupt.
Yeah.
May I ask, like, what do you think of the difference between this in-context learning and meta learning? So it seems to me that the training is, you train the model to learn, right?
Exactly. So in-context learning is actually is basically like I would not say it's like kind of it's basically a subset of meta learning.
Okay.
Yeah, in-context
Yeah,
learning is a subset of meta learning. So this is definitely like meta learning, but I think people use meta learning for like deep neural operator learning. But after this like this meta learning stuff, you can like take advantage of the similarities across different tasks, but you still need to fine tune stuff. So in context learning, the characteristic of in context learning is that you don't really need to fine tune anything at all after the training.
Yeah, I see. Yeah, thank you.
Yeah, look, I also have a question.
Go ahead, George.
Yeah.
Sorry, partners. So, because some data also was, it hasn't published it. It was basically training DeepNet to learn different PDs, let's say, but it was the same class of PDs. What you're showing here, in other words, let's say you have reaction diffusion equations, and you just change the reaction terms, right? So you're thinking about the Fisher equation and so on. Now, you are in this example, what you have is that you're training the operator to become a polymath, to learn all sorts of different equations, which are, because I see an ODE, then I see a diffusion reaction, then I see something totally different, and so on. So you want the operator to learn everything, to be like a general AGI type.
Exactly. That's very good. That's very good work. So essentially, in our published paper, we use one model to solve like 19 types of problems simultaneously. So you have different ODs, different PDEs, and even mean field control problems. 19 problems.
And what's the advantage of this? Is this because when you have the same class of equations, right? Reaction diffusion. You have synergistic learning, which is like in the paper Gatto in the architecture Gatto of Google, they imply, at least, I don't know if they prove theoretically didn't, but they imply that they had 600 tasks, but they were doing synergistic learning. What is the synergy here if I solve an ODE and the Maxwell equations? Is there synergy? I don't see it.
Okay, so you are basically talking about like what is the commonality share across this kind of tasks, right? So so in this, for example, I would say firstly, it's kind of hard to tell really, like say like what's the connection between ODE, like for example ODE2 and this linear reaction diffusion equation. But for example, it might be like the solution field could be similar for different like types of operators, like input function, output function. Although the operator can be totally different, but the input function could be similar, right? And secondly, I'm really looking forward to see, like, say, okay, what if we have trained like some ODs and some PDs? Now we encountered a new OD or PDE. Can we just like handle this kind of new OD or PDE without any fine tuning? So that is something I'm looking forward to see. So essentially, once your task become more and more broader and become more and more diverse, we are expecting like see some like
the point,
generalization.
Can I just say, if you multitasking, if you don't have a synergy between the tasks, you might as well have what LeCun calls task specific intelligence, not generalized intelligence, because generalized intelligence is expensive. And so on. But task-specific intelligence, which means an operator for all these, would be good, because from one OD to the other you can learn. But from an OD to PD, is there a synergy? That's why, unless there is a synergy, I cannot see why you need to have that. The inputs and outputs are sort of relatively cheap arguments.
Sorry, I'm not sure if I get your idea correctly. So what do you mean by synergy, actually?
Synergy.
I think,
the fact that if you learn similar tasks, there's synergy. So therefore, I don't have to double the effort to learn the second task.
Yeah, that is exactly like what I'm trying to convey. So I admit that it's hard to see like the operator of an OD and to see the similarity between OD and PD. I admit that it's kind of hard to see that.
So why you need? That's why I'm asking the motivation for this. Why you need, just because you can do it, or just because it's more efficient at the end?
How can I say? So firstly, I would say, although the operator is is kind of different, but I would say sometimes the input function and output function, this kind of function could have share some similar patterns inside different systems, right. So that is like one reason. And secondly, like when I train on different operations, like some ODs and some PDs, and now when I encounter like a new type of equation, it may be like like something in like, I don't know, another operator which we have never seen before during training. But still, I'm looking forward to seeing that, okay, this model can be generalized to this kind of new tasks. They have generalization over tasks.
Okay, you can proceed. Sorry, Panos had the question, I think.
Sorry. Can you go back to the previous slide, not the one with...
This one.
Yes, this one. Yes. So, hi. This is Panos Tinis from Pacific Northwest National Lab. So you say, I agree that you do not need the fine-tuning. However, there is a price to pay here, because you need, during inference, to learn the new context, right? And to do that, you need these demos, 1, 2, etc., J0 that you have here, and then you add the query. So, okay, first of all, there is the question of where are you going to find these demos, but let's assume that we have them. This second question goes along with what George was asking, that this new context that you want to learn during inference, if you don't do any fine-tuning, this new context should be somehow related to context that it has seen before, because if it has not seen anything like it, unless you use a large neural network so that it can learn the new context, I don't see how knowing the previous context helps.
Okay, so that's definitely very, very good point. So firstly, I want to try to answer your first question about where this example or this context comes from. So this is basically try to mimic the operator learning task. So you train the trained data for the operator learning basically comes into the in this kind of demos or examples. Anyway.
Right.
Anyway.
I agree. Yes.
As for your second question, like this inference during this inference, this data has to, or this content has to share similarity between the training data. That's exactly true. So but in our experiments, we also see some kind of generalization. So it can be generalized to some out of distribution operators.
And this goes along what George asked. How much can you generalize? How far away can you go from what you had in your training? Let's say operators.
We'll talk about it later in detail. So I can try to give some early answer. So we have seen some like generalization on the operator parameters. When I say operator parameter, I'm talking about, okay, for example, here this kind of numbers are the parameters that specify the operator, and we have seen like decent generalization on this operator. But for a completely new type of equation, due to our limited size, we didn't really see very perfect generalization. But we can see the trend that as we increase the data, the data size and diversity of data, we can see like better generalization. Although in the end it's still not perfect because of limited size.
Yeah, thank you. That makes sense. Thank you. Thanks.
Hi, Yang Liu. I also get 2 questions for you. So first one is that I see that in your training stage, in each of the training step, you only train on the single query. Is this for simplification, or you actually did more?
This is just for the for demonstration. Actually, in really we actually do it in parallel. Don't worry. And I will say that this prediction actually can be evaluated in parallel. Don't worry.
Okay, I see. And the second one is that could you please go back to the outline?
Yes.
In the inference stage, I see that you have used a lot of condition and QI pair. And indeed, in the real world, if you have a lot of these things, maybe you can already find some patterns or by simple methods. So what if I do not have so many condition QI pair data?
So
can you input something like yes?
Yeah, maybe you can finish your question, but I think
So for instance, if I only know the formulation of this PDE, can I just input, like you said, input text into this way instead of putting a lot of data?
That's exactly what I'm doing here.
Oh, I see. Okay.
Yeah.
So you can kind of replace this bunch of data with a simple caption.
Yeah.
Okay.
Yeah, we'll talk about it later. Yeah.
Okay. Thank you. Thank you very much.
We actually in the same page. Yeah. Okay. So shall we continue? Okay. Yeah. So here I want to basically like try to show the analogy between the icon and the GPT. So in the icon, we basically like input some here's like some examples and the question, and in the language models. Well, this is basically like just an example comes from the GPT-3 paper. So you can pass the description, and you can even give some examples and the question. And the generative language model should give you the translation of cheese into French. Analogy between the in-context operator analogy and the generative language model. So yeah, here's the model architecture. It's actually a transformer-based architecture. So basically, actually, it's like a encoder-decoder architecture. The encoder is like okay, you have different examples. Example 1, example J, and you have the question, and you have the question condition, and then you feed all of them into the transformer encoder. So they get a sequence of embeddings which represent the operation and the question. And in particular, each token here, each column is like a token. It consists of the key and the value and the index. What is key v? So essentially to represent one function, I'm using like a set of key and values. The key is the input of the function, and the value is the output of the function. So this is a bit technical. So if you really want like more details, I can show you the paper. But I just want to show that the goal the goal is that okay, the number of the input function is flexible. The number of position of data points for each function are flexible, and permutation invariant to these data points. And the predicted question QI function can be evaluated everywhere. So it's not just like a vector representation of function. You can basically like input X, just like pins and default net. Okay? And this kind of evaluations and prediction can be performed in parallel. So we later simplified and improved the model, but this probably still holds. Yeah, so here like we try to solve these 19 problems with a single neural network. This actually is not a very large one. It's just like 30 million parameters. Because due to the limited computational resources. Okay.
So which one is used for training and which one is used for testing in this?
Oh, So in this case, we use all of them for training, and for testing, we tested like the in distribution operators, and we also test some audio distribution operators. We'll see detail later, but again, we use them all for training. We also designed another one only used for testing. I will also show you results later. Yeah. So this is like just selected like OD and PD problems. This is like the OD3 this is oscillator damped oscillator.
Yeah, I have a question.
Yeah.
How about the domain, the input domain? Because all these domains are 0 to 1, and I want to transfer. Let's say I transfer from a square to a triangle, or from a square to a square with 2 holes. How about that?
We haven't tried that in our experiments. I admitted that. But I mean, this framework definitely supports that. So the idea is that I really want to. I was definitely very happy to like.
But I'm looking at the conditions, and I can see that you have very carefully selected the time domain.
It's not very carefully. It's just like a full convenience, like from 0 to 1. You can do that. Like actually, if you take a look at the OD, you will see that we actually like have different lengths. So for example, in this case, you have the for this is like one function. It's from 0 to like 0.9, and this one is only from 0 to 0, like say 0.85. It can be random. The domain is definitely not like say carefully selected. It's just for simplicity.
Okay.
Yeah, and also you can see that this selection, this point is like data point selection is basically also like random. I didn't really do anything like fine tuning the data. I didn't do that. Here basically like the gray dots are the data examples used in the data used in the prompt, and the blue dots are the data in the question condition, and the red dots is a prediction with this black line as the ground truth, and you can see basically they overlap with each other. So the prediction is good. This is for the 1D. Here's another one. It's for the mean field control problem, which is the thing I really like. So essentially, the mean field control problem is like, say, I want given like the okay. So this is the governing transport equation. So you have diffusion and some like brief term, and you want to minimize the terminal cost as well as some like kinetic energy, something like that. Yeah, so here I basically provided the neural network of the model with like 3 examples of question and the QI, and they should share the same terminal cost as the unknown parameter in the operator. So this operator is determined by the terminal cost, So now, okay, so just give me like this data. The model managed to infer the terminal cost, and then now given this new question condition, it managed to predict the downstream density field like this. This is a ground truth, and this is prediction, and this is the area. So this area is basically like even you take the average, should be like less than 2%. So this is, I would say, this is a kind of like standard mean field control problem. So you try to infer the like say the terminal cost, and then apply to the new condition. Okay. This is like say the 1D to 1D to sorry, the 2D to 2D prediction. But here we also have like 1D to 1D. 1D yes, this is 1D to 1D basically means that okay, you only have the initial condition, and you want to predict the the terminal distribution.
Hi, Liuyang, this is Somdata. I have a quick question.
Yeah.
I'm Somdata from the Crunch group. I wanted to know, like, how do you make the network identify which equation you're trying to solve? Okay. So firstly, so the model identifies the operator from the input prompts, like these kind of examples. So the example should
tell them model the operator. And secondly, I will say this model is not really looking into the equation. It only looking into operator. If, for example, like maybe different equation can lead to the same operator. I'm not sure, but even if there are some cases, then the model will not distinguish different equations. It will only care about the operator that maps the condition function to the QF function.
So your training has a different set of so the equation list that you were showing, the training can have, like, the training has all these equations, but your testing, does it come from these same set of equations, or is it a different equation that you are trying to run an operator for?
So the results here, these results are all comes from this 19 problem types. Then they are all used for training. And during testing, but I mean during testing, we are, although the problem, okay, this is something I didn't really make it back. Although the problem type is seen before, but the parameter is never seen before. The parameter means this operator, like you have different A1, A2, different K, and different like terminal costs. These are the this operator, and this parameter is never seen in the training.
But I think, Yang Lu, I think what you're doing is, like to answer some data's question, I think your prompt is such that it has to have the keywords in one of these 1 to 19 types of equations. Otherwise, you.
No, there's no so-called like keywords. It's basically
can you give a specific one example where you have the query, the prompt, everything? Because right now it looks a little magic.
Yeah, I mean, like for example, this is last one, right? I didn't specify anything like this, like this is the type 2 or type, this is a PD. I didn't specify any of this. All the inputs are here.
What are the inputs? I don't see the inputs. That's why I'm making specific for us.
So like the input in this case is like, okay, this operator basically maps the U to K, right? So U to K.
But you have another 18 equations that do the same thing. Or another 10 equations that do the same thing. Why did it pick this one?
This is just an example. Well, I have another 2 examples here.
No. So that's why we don't understand. I think you have to, when you say you example, you sort of force it to do that example. And then you just do the usual map of the operators. That's the thing that, otherwise it's the same thing that we do every day with the operators.
Forcing.
You're forcing to use this equation. How does it know? That's what the question that some data asked. How does it know to use this equation to map? Not the equation above.
Okay, the model just identifies the operator. Okay, so he's able to identify operators from these examples, right?
How?
Can I say something? I think it will help. What is called unknown operator on the right column, it's still unknown. It's never forced. What the demos have for different K of X, for different U, it has as output a different K, and it uses as demos these pairs to learn the context of this unknown operator, but it never actually learns the operator. It only learns the mapping from condition to Q of I.
Exactly.
Yeah, that's fine, Panos. Panos, that's fine. But let me change the problem a little bit. So I have this, what he shows is a diffusion reaction equation, right? How about if I use diffusion advection reaction equation, and I have also the same pairs? The only thing that there is an operator with an extra term, the advection term, but the mapping is still from K to U or from U to K.
Yep.
What do you do in that case?
Yeah, that's your question. That how can it, if it can generalize to other problems?
How can it differentiate between two different?
So
otherwise, it's
Professor. It can differentiate, because in that case, then the map to U to K would also change. For the same input U, the K would be different, right? So it can tell the difference.
Yeah, if you have an advection reaction diffusion equation, then the K will be different now with the same U. The U can be the same.
Exactly.
No, there's no way. No.
Or the other way around, yes.
There's no way it can differentiate because you can have different values in the range. You can have if you have a wide range, you can have multiplicity. So there's no way that you can differentiate unless you force it.
I get a little bit confused. So maybe we can think in this way. So now, like suppose we are doing like operator learning, just like very just like deep net. And now we have like two operators. That one is like this one, another one is like the reaction diffusion one, just like mentioned. So we have two different data sets, right? So how can
the data set, Yang, the data sets, the mappings may be identical, but the operators are different.
Yes.
The mappings can be identical. I choose the numbers I can write down for you. It just so happens that the advection term is there, it pushes it, but it gets into a range of parameters and mappings that are in the same range. So that's not enough to differentiate.
Okay, so I think I get confused about what you mean by the map, because operator is a mapping itself, right? You're talking about the equation is different. I mean, so my understanding is like the operator is just the mapping, and of course, like it's the same, like different equation can correspond to the same operator. That is true, and we will definitely not like distinguish it. And I would say that is good because in the problem setup we only care about the mapping. We don't really care about the equation.
Yanglu, in the picture that you show here, unknown operator 1. For the unknown operator 1, what are you mapping and to what are you mapping? Like what is your input and what is your output?
So in this one, it's like the input is like the C, the control, and the output is the U, the C, the state, which are both functions.
Okay, and in operator 2, it's the same thing, right?
No, actually, in the operator 2 is I think is the input is U actually. The condition is the input and the QI is the output. So in this case, it's like try to identify the right-hand side from U.
So you have one. So in context operator learning typically identifies if you're doing a forward problem or an inverse problem. If you are choosing, let's say you're doing two forward problems, two inverse problems where you're mapping from C to U, and you're using two different equations. Your input C is the same. How do you get different U? Because you're solving two different equations.
Yeah, different. Then it should be reflected in the examples, right? That should be reflected in the examples. If you have different operator or different equation, then the example would be different. I mean the input is not just the condition for this for the current system. It's also like some examples.
So you never have an unseen example. That's what you want to say?
No. I can have some unseen example in the inference, but it's just how can I say? But the model managed to extract the mapping from the examples and then apply it to the condition, new question condition.
Do you retrain in the inference stage?
No, it didn't retrain. The model is trained to be a learner, so it obtains the ability to extract the mapping from the examples and then apply to the condition, to the question condition.
Okay, probably I'll read the paper. Thank you, Yanglu.
Yeah. I mean, I think this is a very good question. So, so I think this is a very good question because I think it really like try to help me also like to summarize what is the ability of this model. The ability of this model is able to extract the map from these examples. When I say extract, it basically says that it identifies it. Of course, it identifies from like a distribution, like a group of them, but it managed to identify it from the examples and then apply to the new condition.
Maybe if I put this question like that, like let's say, can this model learn the case equation and the like reaction diffusion equation at once, like in one?
Okay, that's a very good question. So the short answer is not for now. No, for now. But the long question is, firstly, we have seen some generalization to audio distribution. Okay, we'll see that. We have seen some like audio distribution operators. It can generalize very well to some audio distribution operator. But for the new equation of new form, we can only see the decreasing trend for now. It's not perfect, but I think it's basically limited to the size of a neural network and the size of training. I mean, even for the language model in the early stage, you cannot really use it to do like some out distribution tasks. But now, as the model becomes larger, we can see that it's almost like a generalist, like general AI.
Okay.
Yeah. So that's why I say it's towards a large scientific learning model. It's not large scientific models. It's towards large scientific models. Anyway. Yeah. Yeah. Let's continue. Yeah. Here I like one model for 19 types of problems. Yeah. So by the way, each type of problem you still have like a continuous spectrum of operators. For one type, even in the one type, there's like infinite number of operators governed by these parameters. And then you take the average. You have like a number of examples from 1 to 5, and so in the end you have this is what we get. Okay. So with like 5 examples, the relative error go down to about 1% to 5%. Well, you may ask like why 5 examples is good enough. I will have a very detailed discussion in the end. But
this example here is the example in the prompt context.
In the context. Exactly. Very good.
Then what's your training data set size? You have 19 for
very
each
good
one.
Question. Very good question. So for each one, we have like 1,000 operators. And then for each operator, we have like 100 pairs of examples. So it's like 19 by 1,000 operators in total. And for each operator, we have 100 examples.
Okay.
Yeah. But I would say this is still kind of sparse for some challenging problems, because for example, in this example, the mean field control, the parameter is like a function. So even like 1,000 function is still sparse. Yeah. So yeah, this is basically like what you are showing here is like the performance on testing data set. Okay, on testing data set, not on training. But the distribution is the same. It's in distribution. Okay, in distribution. But now I will talk about like some generalization. So what about so here still the same problem, mean field control problem. So if we increase the number of data points in each condition QI function, the error decrease finally converges below 1%. So here I want to change the number of key value pairs in each condition of QI function. So what is key value pairs? That's exactly how many data points you have in the function. So the number of data points here, data points here. And you can see that. So this red region is the region we use usually in training. That is from 40 to 50 here, but it generalized much beyond this region and still show a clear decreasing trend. So this is a super resolution or sub resolution, or like generalization to different number of data points in the function. By the way, this one is basically like enabled by the transformer, because transformer enables you to have like a kind of flexible input length, right? And this is audio distribution operator. So I basically talk about the OD and the P, one OD and one PD, the forward and the inverse. So what does this stuff mean? So here the axes are the parameters in the operator. Okay? So each point here should represent an operator. Okay, and the black rectangle are the training region for the operator parameters. So in the training region, we only see the parameters in this rectangle, but you can see that it can generalize very well to some to operator beyond the training region. Okay, so and okay, this is like
But I
about,
have
yeah,
I have a question. So in previous slide, you have a number of examples of 5 for testing, right? During the then why in the training you need 100?
Oh,
Can we do
that's
also
a very good
5
question.
to 100?
That's very good. So 100 basically I randomly sample 100, randomly sample 5 from 100. So it's a 100 basically like a pool. So just a random sample from. I never tried try to fix like one, try to fix them. So it's basically trying to add more randomness. I'm not sure if you're happy with the answer. Yeah, just trying to add more randomness. Yeah. So generalization of two equations of a new form. Yeah, so basically this is the OD2. Okay, so in this OD, this is OD, and this is OD3. And now we design a new OD, not in training. So this is basically a combination of OD2 and OD3. Looks like this. It borrows this term, and this term into the new to build a new right hand side. And okay, this is a forward inverse problem, but we can just focus on the forward problem, for example. And if you only have OD2 or OD12, which are basically similar, this is what you have. So the area is this large. And now you will have a further add OD3 here. OD2 and 3, you have the green one here. And you have if you have OD1, 2, 3, put them together, you have the blue one here. So so I would say we see like the decreasing trend as the training data set become larger and more diversified. So I would say this is the preliminary evidence of learning operators for equation of a new form that we never see in the training data. Yeah. Also, I want to pause here to ask whether you have any questions. Okay, great. So so we next also propose like multimodal in context operator learning. The basic improvement is that first we simplified the model architecture. There's only one transformer now. And secondly, we have basically like fewer parameters with higher accuracy. And most importantly, we have multimodal paradigm. So that apart from function examples, we can optionally take captions as input. What is caption? These are the text that integrates human knowledge in natural language and equations. I think this is the question asked by Zhongren, right? So we can specify, oh, this is OD, blah 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 blah, and the boundary condition is blah 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 blah, and so basically tells what this operation is.
But if I have the caption, why do I still need the examples?
Then we have zero shot. We'll see that later. Then we can have like zero shot learning.
Okay.
Yeah. Yeah, this is the architecture. There's like only one model here. One transformer here. But this transformer has very complicated attention mask to enable the in context operator learning. You can train from scratch or directly fine-tune existing language model. And you can utilize existing techniques and tools develop language models. You can, and I would say it broadens the capability of language model to scientific machine learning tasks. So I think this basically like open a new avenue for the application of language models, which I believe is good. So this is very technical. If you're interested, I can explain you later. So I want to compare the icon AM, so the new model architecture, with the encoder decoder icon, which is the first version. For the single model, is like there's no caption, just the oriented level. So you can see the relative error, we are consistent better. So this model architecture is much better. Okay, I think this is a question of Lulu. So now with these captions, if this caption is like precise, that it already really tells us all about this operation, then we don't really need examples at all. So we can perform like zero shot learning. But I would say even with a vague caption, it identifies the type of the problem. Okay, it still can help us like decrease the error a little bit, not really a little bit, like by half. For example, this vague caption, it tells the type, but didn't tell us the exact parameters. So you cannot identify the operator. You can just operate. Like you can just say it belongs to this family, but it still helps. Well, this one says that okay, after all these numerical tasks, the language model also have better understanding of the text. So before okay, oh okay, I forgot to say that. By the way, this result comes from like fine-tuning GPT-2 model. Okay, I'm literally fine-tuning a GPT-2 model for this multimodal learning. The GPT-2 model is actually kind of it's actually like 130 million parameters. But it's still like I'll just say like 100 smaller times than like modern language model. Still very tiny one. Okay, so the standard GPT-2 model, if you feed, so this is like the just for simplicity, I selected like 4 types of captions and try to feed into the standard GPT-2 model to get the sentence embedding, the embedding of these captions, and you visualize it with TSNE to visualize looks like this. So they are basically mixed together, meaning that the standard GPT cannot really tell the difference between these captions. Okay, the standard GPT cannot tell the difference, but after the fine tuning with this numerical task, icon numerical task, I would say these clusters are much better separated. In our paper, we have a like much rigorous comparison with some quantified metric to support that. So the conclusion is that
here I see that they still cannot distinguish between an OD and a PD.
It cannot do very. You have some mixture.
Yeah, there.
I agree. But I would say so. Firstly, this is like you're trying to. So embedding is actually like 700 dimensions. It's about 700 dimensions, and then you map it into 2D. Yeah, sometimes you just cannot tell them apart.
Well, GPT-4 can do it, but I think you're training the wrong model. You should have at least try the 3.5.
You can give me like money that I can train it for you.
No, you have money. You have money at UCLA. You're rich. But the reason I'm saying that is because we have something which actually does that. But it's not. It's a commercial product. It's not.
Yeah, I would totally agree that like if you have like larger a better model, you can definitely do much better. So I'm here just like try to do some like preliminary studies that okay, this kind of numerical tasking actually. So here it is. So how can this model really understand the equations of mathematics? You have to. So what I'm talking here is that okay, you should ask this model to apply this equation to some real data. And actually, this kind of numerical text helps the model to understand what do you mean by OD, what do you mean by PD. Yeah, but yeah, so I would say that our computational resources is rather limited. So GPT-2 is what we can do. Thank you. Questions? Okay. What time is it? Okay, we are running out of time, so I will just go through this very quickly. So this is basically like a forward backward prediction of conservation loss. So in particular, I'm looking for this equation. And we can define the backward operator, which maps from like this instance to like 0.1 time later. You can also do the backward, by the way. But the challenge is that backward operation is not unique for this kind of equation. The challenges are discontinuities and non-uniqueness. So so the discontinuity, yeah. So here's I'm just showing the example of that ugly. So even if the initial is continuous, as we go on, it's basically like discontinuous. So this is a challenge. But I would say the icon model performs very well here. So so this is so condition and the in blue and the ground truth in black and the prediction, which is in the dashed red, and basically you can see that they're kind of consistent. Okay, this is for this equation, and this, here I've shown another 2 examples. They'll perform kind of well. For the backward one is actually a little bit more interesting because the prediction is different from the labels because this backward operator is not unique. But if we apply the exact forward operator to the backward prediction, just like forward simulation, the forward simulation overlaps with the input condition. So it's like the blue one and the green one. So the conclusion is that although the prediction is different from label, but it's actually also a feasible solution. The solution is not unique. The label is one of them. Our prediction is just another one of them. And here are just like more examples. Okay. So yeah, I would say the inconsistency between the label and the prediction is very common. But I'm glad to see that the condition and the forward simulation with the green one and the blue one, they are still very consistent. So here's the relative error. Yeah, basically like 1%. This backward is larger, but the consistency is good. So like 1% error. Again, so all the predictions, including the forward and backward prediction for different equations, are given by the single neural network. Yeah, here in the end, I want to have a discussion. So why a few examples are sufficient to learn operators? Basically because only need to learn the operator for a certain distribution of these conditions. So like the input of this operator is basically not like any function. It's basically still like a certain distribution. And also, we leverage the commonality shared in training and testing operators so that the icon only need to identify the equation and the hidden parameters. So that is also makes things easier because I would say the family here is like just 19. It's still not too much. So a few examples would be enough for the icon to identify the equation and the hidden parameters. But I admit that for larger family operators, it definitely requires more examples, as well as a larger model with more training costs. What's next? So I really want to scale up. I want to scale up to large language models. So historically, scaling up large language models improves generalization, even lead to emergent abilities beyond the human expectations. So numerical task is still like a weak spot in the current AI ecosystem, and we anticipate that the possibility of AI for general numerical tasks with larger icon models. Yeah, that's all, basically. Thank you.
Thank you, Yanlu, for
your thank you.
Yeah, it has been a really heated discussion among this presentation. Yeah. Do we have questions from the audience?
Can I ask one?
Yeah, please.
Hi, Yang Liu.
Hi, Xing. Nice to see you.
What a great talk. I wonder, have you tried some examples with the bifurcation? So that I wonder whether this model can capture the bifurcation behavior. So that is quite.
You mean bifurcation of ODE?
Yes. So dynamical system.
Yeah,
because
dynamic system.
Because that is the quite good. I thought that's quite good example that in the context what you icon model, because you have a collected snapshots and before, so that your input shall be before the bifurcation happen, and wonder if your model can predict this behavior.
Yeah, I think that's a very good question. You know, so I think the challenge of this stuff, I'm not sure if my understanding is correct, but the challenge stuff is not uniqueness, right? Yeah, please. Yeah, I think maybe my understanding of bifurcation.
I can tell you the answer. The answer is that it cannot, and some data has actually published that. You need to add an extra terms in the for the shift of distribution. You cannot go through bifurcations. If the standard operator cannot, then this will not.
That's what I suspect. So
there's no magic. I mean, there's no magic. Even with the transformer there, it doesn't matter. Some data, what do you think?
Yeah,
you can try that. You try to do that and without.
No, I would totally agree that like you cannot do. So for now, the output is still like one function, so you cannot do that for now. But yeah.
But some data has published a paper in Nature Machine Intelligence where she shows that if you add something else to the the conditional shift basically in the regression loss, you get it for the brucellator dynamics. She goes from a limit point to a fixed point, from a limit cycle to a fixed point, and that's a clear.
Okay. So that's very okay. Congratulations for the new paper. So if I try to like tackle this stuff, I would say I mean, okay, this stuff is also like our like very baby version. So so what about like distribution of output? Like what about the output with uncertainty? What about like non-unique like multimodal distribution of output? That is definitely like we can try like in the future. Yeah.
And also for this one in the context operator learning, we have done something at Crunch where we are trying to learn multiple operators at one time, but we are enforcing the PDE. So that the operator identifies which PDE it is solving at a particular time. Given you have the same inputs, you need different outputs. We haven't published it yet, but we do have something. We are writing it up.
I somehow didn't really get your point. So
so let's say you go back to your equation table that you have.
Yeah.
The equation table with lots of with 19.
Equation table, yeah, equation table, yeah.
Yeah. If you see if you see your problem description 1 and 3, so in both of them you're trying to learn parameters A1 and A2, and you have pretty much the same conditions and the same quantities of interest, but your equations are different. How do you identify these two equations?
Well, I get confused. So if your condition and QI are just identical, just like this map is for the same condition, you always get the same QI. I will just view it as like the same operator. For example, in this case, I would say like this case, problem 1 and problem 3. Okay, so what if like say like A1 just close to let's say A1 just close to 0, and the equation looks different, but the operator is just the same. Then we just view it as the same operator. We don't really care about the equation.
But
that's the danger. That's some data. That's the danger, because imagine if you change the range that you have, then you get totally nonsense. But and I have a question for you, because that's sort of the.
George, I want to like I disagree with that. This is this with no hand. I mean, like I agree that like for the given like data, we may not be able to identify the operator, but this is just like the training data inside the like deep learning, right? In the training data you cannot distinguish it. Then in the testing you just cannot distinguish. But we can also like we basically like put the training data inside the input. So
I agree with that. But I have a question about the cost. That's fine. No problem. No disagreement on that. I have a question about the cost, because there is an emerging divide between those who believe in AGI and people like LeCun, who don't believe in AGI. They believe in task-oriented AI.
Very good question. So
but let me ask the question. So if we go, let's stare at the 19 equations that you have. If I train 19 DPONets or FNOs or what LNOs, whatever. If I train 19 operator networks,
so the answer,
how much cost will take versus the cost that you spend, and what is the benefit? Because I don't see
very good question.
I don't see the value for the return for my dollar.
Okay. So firstly,
it's cute, but it's cute and so on, and we do that too, to use GPT. But it's not. I don't see the value for the dollar, and I don't.
Very good question.
About scientific machine learning, which is a little bit of premature.
Very good question. Very good question. Firstly, the training of all this stuff takes like 1.5 day on two 4090 GPU. 4090 GPU. Okay, 1.5 day on 4090 GPU. 4090 GPU. I would say, George, I know that you are super rich, so you have You have A100. We don't even have that. And secondly, I will ask the question: how many operators do we have in this list? It's not 19. It's infinite.
No.
Even for one
infinite,
type, even for no. Even
can I count your operators? Can I count your operators?
Try count that. I will guarantee you that it's 100. It's like infinite.
Okay.
It's
First,
infinite.
second, third is the same. So that's one. Then you have the fourth one. Then you have a fifth one, and sixth one is the same, and the seventh one. So that's like 5. And then you have the last one. So you have 6 operators.
Professor, I would say
if I change the range,
even for this line, is infinite, because for every G, for every terminal cost, you have an operator, and this terminal cost is a random function. So for every G, for every function, you have an operator, and we have a random function of G. So it's infinite operators.
Just to clarify, so we can consider multiple input operator, not necessarily a single input operator.
Exactly.
But however, this G is not known. Okay, this G is not known.
Yeah, G is a random function. Yes.
It's not known. It's not given in data. You have learned that from data.
I think, Yang Liu, I think we maybe you forgot what deponent can do. Deponent can you can change the range of kx and I make it 0. Then I don't have reaction. So it's the same operator. I think we're talking different language now. Just to disagree. There's no disagreement that the first equation, the second equation, the third equation are exactly the same.
Yeah, you can say that the same. But I mean, at least we can. How can you use one deponent to tackle OD, PD, and mean field control? I mean, they have different shit. They even have different dimensions.
I know you can do that. I know you can do that, and it's commendable. It's commendable. The question is, what's the purpose? Because either you go for accuracy or cost, but that relates to the synergistic question that I asked. So
I think firstly, I think the cost is that okay, even for this stuff, for this mean field control problem, every G will lead to a different like this. So for example, okay, how can I do this stuff with DeepONet? So this is data we have. Okay, we have 3 data here. One, this is one function, a second function. This is one function input, one function output, the second function input, second function output, third function input, third function output. So that is the 3 data we have for DeepONet. Okay, and we can feed that into the new into DeepONet, and DeepONet will learn the operator and apply to this one, and predict the output function. Okay, that is what it would do with DeepONet. And what if I change the terminal cost? Then you don't know the terminal cost, right? So you need to train another DeepONet for that, correct?
Basically, a DeepONet with 2 branches. One for terminal cost, one for the
terminal cost is unknown. Terminal cost is not in the data. Terminal cost is not in the data.
But he can train for a range in the first place. He can train for a range.
I'm not sure what you mean by range. It's not in the data. It's not even in the data. I mean, for every terminal cost you will define the operator. Okay, if the terminal cost changes, then this map changes. You definitely need another operator, like to describe this map, right?
No. So the operator is mapping from the product of 2 banana spaces to the output banana space.
Okay.
Right.
Lulu, so essentially, I think I got your point. You're basically saying that this operator maps this stuff and the terminal cost to this stuff, right?
Yes.
Yeah, you're definitely correct. You're definitely correct here. But my point is, you cannot really put everything. You cannot really put like everything inside the input of this operator. So in reality, because you don't have data for the terminal cost. So what you can have is only to have this as input.
You can do transfer learning. You have read the paper of some data. That's why you don't know. You can do transfer learning from one case to the other, which basically costs 1% or 2% of the previous.
Yeah, very good. So I think I cited
in fact, let me ask you this. Let me ask you this. If I want to change the domain, not because you're doing something which is convenient for you, but that's not my. I'm a customer. I want to change it. So I want you to go from a domain that is a square domain to a triangular domain. So, so g of x will be the same, but the domain will be triangular. How do you do that?
So if I really want to do that,
because
would like to.
That's what I'm saying. With transfer learning, with 2% of the cost, you can do transfer learning, and you can do it. Transfer learning plus penalized and conditional. So it depends. I'm not saying that it's not a bad idea. I'm just saying that you haven't compared it with anything that we know, and it sounds magic and sexy because it's ChatGPT. But at the end of the day, unless in multitasking, unless there's synergies, and you can prove it through cost, I don't see the motivation being valid. Apart from the point that is, okay, I can do it or so on. Because you made a big statement about scientific machine learning that is changing the paradigm or something like that. And I think that that's like a very, very ambitious statement.
So firstly, if you I would say this paper. I would say this paper is trying to prove the stability like without any fine tuning. So I know that you can like if we switch the terminal cost. For example, in this case, if you switch the terminal cost a little bit, well, you can fine tune that like with like 100% of terminal cost. What if we change the terminal cost a lot? I don't know how much. I don't know what happened, but okay. Let's suppose you can save like you can have like 10% of computation cost, but here it's like just no fine tuning at all, just like one forward, you solve it. And for what if like you want to change the domain? I would say maybe okay in the training data. What if in the training data we have different domains, right? What if the change of domains already is this kind of randomness is also reflected in the training stage? Then I would say it will also be reflected here, I think.
I don't think you can do change of geometry. Impossible because there's permutations. You cannot anticipate. If I put a hole or if I put a triangular hole or rectangular hole, if I make it around the edges of the domain, or if I add another block of the domain, I don't think you can anticipate that. So you have to do transfer learning. And the question is,
exactly my third point. So if you have something like you just cannot handle with the existing model, you can still fine tune it. But my point is like now you are approximating like a distribution of operators, not just one of them. So even like you want to do the fine tuning, I would say it might be like more adaptive. I would say, yeah.
So the question that I ask you, maybe you can consider it and think about it, about the synergistic learning, because multitasking implies that. If you go back to the Gatto paper,
exactly.
That's what they mean. And if you look at the appendix of that paper, that's what they imply, although they actually cannot prove it. That it's easier to learn a third task than it's easier in terms of the cost than learning 3 independent tasks.
Yeah. So that's,
are you claiming that? Are you claiming that or not?
I'm claiming that. So we are basically leveraging combinatorial share across various tasks to reduce data requirement, at least to reduce data requirement, right?
Yeah. Yes. Data and cost are the same thing.
Yeah. So we're in the same page. Yeah. Well, I definitely will agree with that. Yes, thank you.
Do we have any other questions from the audience? Any comments? No?
Well, thank you very much, Yang Lu. Thanks for coming back, and thanks for the great talk. I may disagree on some points, but that doesn't mean that I don't like the work.
Yeah. So, George, please also forgive me. I get kind of too excited during talk, but I definitely like. So I basically like want to like share what I'm doing, and also we can like work together on this like in the future, right? It's like yeah, I mean this is like a huge I just want to there's a huge opportunity in this like new direction.
Yeah, great new direction.
Yeah.
Lulu, do you have any other questions?
Oh yeah, one last question. I currently training the large models. Seems to me it's too expensive. I don't have resource at here. Probably you have resource at UCLA.
I can guarantee you that my resource is less than you. So I only have like 2 4090 GPUs.
No, Stanley should have a large cluster or something, right?
Not really. So that's
Not
why
really?
I'm trying. No. That's why I'm. So when I say I have, I mean Stan have.
But in your last slide is the future direction. So I'm just curious whether you are really doing this or.
Oh, right. So I'm basically showing this stuff to everyone. So in case someone has a machine. Yeah. So
you look for a venture capitalist, looking for a VC.
Yeah, exactly. I'm looking for someone who can keep me machine. Yeah. So by the way, that's also the reason why I just trained the GPT-2 because I don't know how to train like a larger version.
All right. Thank you very much.
Yeah. Thank you.
Yeah. Thank you, Yanliu. So yeah, we're about to close the session today, and yeah, everyone have a good weekend ahead. And